Okay, welcome back for the second hour. So what we have looked at before the break was the definition of the displacement thickness as a way of estimating what an inviscid flow would feel as the displacement effect of the boundary layer, where essentially the idea is that we just move this slowed down part of the flow or of the boundary layer up here, and then exactly at the point where these two areas are the same, that would then correspond to the displacement thickness delta star. There's also a third way of measuring the boundary layer thickness, and that is something that's called the momentum loss thickness. And that is typically called theta, or also called delta 2. Theta we can interpret in the same way as the displacement thickness, just instead of kind of the momentum, the mass flux, we're talking about the momentum. So it's the added thickness due to the loss of momentum in the boundary layer. And as we will see later on, when we calculate then specific boundary layer profiles, this will then be something that is related to also the friction. Related to the friction close to the wall. And there will be some nice relations between theta and CF, as we will see. I will not go much more into the details of the calculation of, or the interpretation of theta. I'm just saying that the definition of theta, again, motivated by what we have seen for delta star, is the following. It's just U divided by UE times 1 minus U divided by UE integrated in Y. So it's essentially the same definition as we had for delta star, just that we added this one more factor of U divided by UE. And of course, that kind of shows you that there's something about the momentum because we're adding one more velocity component in there. There's one last comment I would like to make to all these boundary or these two boundary layer thicknesses, which are defined based on integrals. And that, of course, is the question of the, so I mean, for delta 1 and delta 2, it's a question of the upper bound in this integral. Because we're, as you can see, in principle, we need to integrate from 0 to infinity. But of course, this is not something that is really practical to be done. Now, as you can see here, we're integrating actually the difference between 1 minus U divided by UE. So we're integrating this very thin difference here. As you can see, as soon as you're above delta 99, this difference becomes very small. So that means that in practice, we can exchange this delta, this infinity by something like delta 99, like an integral boundary layer thickness, maybe 2 delta 99 if you want. And you will get very, very accurate results. So that means for practical purposes, you don't need to integrate to infinity because you know that everything under the integral is actually 0 then. You just need to go high enough, something that is on the order of delta 99, for instance. And of course, it's the same thing also in this case. Okay, so we have now these 3 boundary layer thicknesses, delta 99, delta star, and theta. Actually, before we go further, I would like to ask you, how big are those? Or how do they kind of relate to each other? I have here prepared a poll again. So if we would like to order now this delta star, theta, and delta 99, how would they be ordered when you start with the thickest one? Okay, so I see a lot of answers, and actually most of them are absolutely correct. So delta 99 is always the thickest one. That's why I was also mentioning here, that's kind of the upper bound in the integral. Delta 99 is the thickest boundary layer thickness. So that is larger than. Second one is the displacement thickness, delta star. And then the third one would be theta. So that's kind of also something that you can keep in mind. Theta is the smallest one, then comes delta star, and then comes delta 99. Later on, when we introduce some specific profiles, so the Blasius profile, we will also get some numbers on how thick they really are. I'll not tell you. I mean, delta star potentially is around half of delta 99, and theta is approximately 1/3 or 1/4 of the of delta 99. But we will get some exact numbers later on. But for now, it's important that delta 99 is actually the largest. There is one last thing that I would like to introduce, and that is the ratio between delta star and theta. That is actually something that is called the shape factor. So that's a number that we typically use in boundary layer research. And this shape factor, which can also be called H12, the 1 and 2 relates to the ratio between delta 1 and delta 2, or as we now know, delta star and theta. And this ratio is actually something quite important because it gives you some information on the internal structure of the boundary layer, because it connects essentially the mass and the momentum transfer in the boundary layer. It's not very easy to physically explain why exactly this ratio is important, but as we will see later on, it is actually something that will be connected to the external pressure gradient, or rather, I should say like this: the boundary layer reacts in a way to an external pressure gradient such that it can be measured with help of this shape factor H. For now, this is just a definition. We say H12 is just delta 1 divided by delta 2. Okay, so now we have defined all our boundary layer thicknesses, so we know how to measure boundary layer thicknesses. Now the next, our next job would be to actually calculate this profile, or to find a way of being able to calculate this profile in a good way. So, and I guess that's perhaps the most interesting part now for the rest of today. So, I would say that the chapter would now be the boundary layer profile. How do we calculate that? Well, I guess before we think about that, let's write down what do we actually know? What are the equations that are relevant to us? So we have the continuity equation. du dx plus dv dy is 0. Okay, so we're looking at a 2D case and a steady case. So we have the continuity equation, and then we have the x momentum equation, and of course the y momentum equation. The x momentum equation, if I'm again just talking about the steady case and the 2D case, and I'm using here the approximation by Prandtl, namely that the second derivative in x is actually not relevant to take into. That was what Alessandra was deriving. So the x momentum equation then becomes u times du dx plus v times du dy, which is the same as -1 over rho dp dx plus nu times d squared u dy squared. And the y momentum equation using the Prandtl approximation becomes dp dy is simply 0. So this is what you talked about. That's the Prandtl approximation, or the boundary layer equations. Boundary layer equations. So essentially, we have removed one term here in the viscous term in the x momentum equation, and the y momentum equation just says that the pressure is independent of y. And of course, exactly this independence of y means that the pressure in the end is just a pressure as a function of x. And in that sense, it doesn't matter where we measure the pressure, so it can actually be related to an external input, so an external pressure gradient that is somewhere imposed in the free stream. So the pressure has here the role of an external input. So these are partial differential equations, so that means we actually have some boundary conditions as well. And of course, the boundary conditions are the no-slip boundary conditions. So U at the wall and V at the wall needs to be 0. And we also know that we have some free stream conditions further away, namely that U as an x at any x and y going to infinity, that should be my U of E, or UE of x, so my h velocity. So this set of equations here, that's what I would like to, or what I need to solve in order to be able to calculate my boundary layer profile. So maybe the first comment would be related to this UE of x, because actually that has a nice connection to this external input of the pressure. The pressure can actually be determined by the free stream, and actually what we can do is we can solve the Euler equations by Euler equations in the free stream. Because we know in the free stream, we say that viscosity is not important. So that means that the inviscid approximation with the Euler equations is actually valid. The Euler equations in the free stream become very simple. Namely, it's just UE of x times dUE of x divided by dx. Now I'm writing normal derivatives because I assume that this free stream velocity is only a function of x, so it's not a partial derivative. And that is balanced in the Euler equation just by the pressure. So we have -1 over rho times dp dx, so the streamwise pressure gradient. So this is the Euler equation. And of course, now you can directly see how we can relate the pressure to the velocity in the free stream, namely this dp dx, so the streamwise pressure gradient, is nothing else than minus rho ue due dx. And of course, with this, so if you know your free stream velocity distribution, you can calculate dp dx, and this dp dx is then what actually goes into these equations. And of course, now in terms of, to be consistent, I can write, or I can change this. This would actually be, again, a normal derivative, because p is only a function of x, not of y. So this is kind of the first comment, how we can use the pressure, or how we can calculate the pressure. But now all of this together, so when we have this UE of x, we have p of x, and all of that, this now forms, so this forms a complete mathematical system that can be solved for essentially any type of free stream velocity distribution UE of x. So this can be solved for different UE of x. So just suppose you know when you a certain velocity distribution, you can now go in and solve this system of partial differential equations, and then you have your velocity profile, your boundary layer profile. Now, we are not really much further in determining how to actually calculate. We have now written down the equations and we have this relation between pressure and velocity, but we still don't know how we should actually do that. I guess the key idea here, how to do that, is that we realize that actually boundary layers may have a certain self-similarity in their profiles, not in time and space as before, but between different positions along the plate. I will tell you what I mean with that. So the idea to solve this problem is to use self-similarity. So use self-similarity hypothesis to transform the partial differential equation, so the PDE, into an ODE. So go from the partial differential equation to an ordinary differential equation. So what do I mean now with this self-similarity here? Well, if I'm trying to sketch this, again, we have an X and a Y. We have a boundary layer that kind of grows like this, perhaps. Let's suppose we have a boundary layer profile here. Kind of looks like this. And then we have another boundary layer profile that perhaps looks like this. Now here the free stream velocity is UE of x, and of course here it's also UE of x. Now the idea is that these two profiles, they're actually self-similar. So that means they kind of stretch with, with this length and this velocity and this velocity here. But if I'm kind of scaling them with both this thickness, which I can call delta, and here the UE, these profiles would actually scale with each other. But they would be the same upon rescaling with the velocity and the thickness. So that's the basic idea behind solving or finding solutions to the boundary layer equations. I mean, it's a very simple equation, but of course, it allows you to go from a partial differential equation in x and y into an ordinary differential equation of only one variable. So take a minute and kind of understand this crucial concept. So we would like to scale this thickness and this velocity, and upon rescaling those two quantities, you would get the same profile. So that's the basic idea. Of course, we don't know whether this actually works. Now we need to see whether the equations allow for such a solution. But at least this was the idea that people had at the turn of the century, in the after 1904, and within a few years, I think it was 4 years of the formulation of the boundary layer equation, they also came up with the first solution of the actual boundary layer equations. So now what we're going to do is we're going to use this concept, and let's try to solve now the boundary layer equations. Using exactly this approach. Okay, so now for the next, I don't know, half an hour or so, it will be quite a lot of derivations. I chose to actually do this derivation with you because I really think it's quite instructive to have it, because it shows a nice way of deriving these self-similar solutions. I try to be as accurate as possible as I can with writing my notes, but of course it may be so that I'm doing some mistakes. But now bear with me. I will do it as quick and as painless as possible, but I would still like to go through the whole derivation. So let's try to solve this now. So we have actually we only have two equations. We have the continuity equation and we have the x momentum equation, which are relevant. So if you start with the continuity equation, nabla u is 0. Actually, I think I wrote it like this. Nabla u is 0. And of course, this just means du dx plus dv dy is 0. Now, we know the boundary condition. The boundary condition is that v at the wall is actually 0. With this, we can reformulate the continuity equation in the following way. V of y actually becomes minus the dx of the integral from 0 to y of u dy. I mean, this is I'm just integrating with respect to y the continuity equation. It doesn't help us very much right now, but for now it just tells us that if I know u, so if I know the velocity u profile, I can actually calculate v if I want. So the statement of this equation is that v can be computed by knowing the velocity u. That's kind of it for the time being. So that's the first equation. The second equation that I can use, well, call this the first equation. The second equation that I will use is the streamwise momentum equation. So u du dx plus v u dy is ue due dx. Now I replace the pressure plus nu times d squared u dy squared. So this is the streamwise momentum equation. I call that equation number 2. Now, what I would like to do here is we want to write equation number 2 in terms of the streamwise velocity u, and now I would like to have this as a function of a new similarity variable eta. And this eta, as before when we did it for the Stokes' first problem, this eta should now be a function of both x and y. We don't know yet exactly how this function looks like, but we just know it's a combination of x and y, which then gives me this self-similar solution. So that's now my idea. I would like to rewrite equation 2 such that v disappears, and I write everything as a function of eta. Of course, that means I'm introducing equation 1 into equation number 2. And this now becomes a little bit problematic in writing, so I'm just doing that. U du dx minus, now becomes a bit tricky, d dx of the integral from 0 to y of u dy times du dy. And that should be ue times due dx plus nu times d squared u dy squared. Now I included the expression for v into this equation. And now I have one equation in U where I know that the continuity equation is already included. So here I know that the mass conservation, so what the continuity equation is really doing, so the mass conservation is fulfilled. So I don't have to worry about the continuity equation anymore. So now we somehow need to start defining this f of x and y. And if we now go to this sketch when we introduced this f of y, we can actually kind of see that most probably this similarity variable has something to do with scaling the velocity in the streamwise direction, the u velocity with this u edge. So what I can say now is that let's assume that my f of x, which is this eta, this similarity variable, so this f of eta would be something like u as a function of x and y divided by ue as a function of x. So it would be a scaling of the streamwise velocity. Or in some way we can say it's a non-dimensional dimensional, boy, that doesn't look good, dimensional velocity. Now, I guess this is a reasonable assumption that we can make. The only thing that we don't know yet is this eta, so how we relate x and y to eta, but this will come later. Now at least we know how the u velocity is being scaled. What I will also do here is I will actually call this to be f prime. So I'll say that this is the first derivative of f. For now, this is just a definition, and I guess we will see later why it's actually useful to call this to be f prime and not f. But of course, we could also now continue the derivation with just f and then realize later on that we need to change it to f prime. But for now, we just say that we define f prime is defined in this way. That, of course, also means that my boundary conditions now need to be changed to be written in f and not in u anymore. Of course, my boundary condition at the wall, well, at y being 0, where I can say that this would correspond to my non-dimensional variable, eta to be 0, and that means that f prime of 0 would be 0. This actually would be equation number 3. At y going to infinity, then I would also assume that my eta is going to infinity, my non-dimensional coordinate, and there. Now the beautiful thing here is that here f prime of infinity would then become simply 1. So now I have transformed also my boundary condition into this non-dimensional form of f. What now remains to be done is I need to now go through all the derivatives that I have in my equation number 2 here, or well, equation number 3. My equation number 3. So I need to replace all the derivatives that appear in equation number 3 as functions of f and eta. As soon as I've done that, then I can start to see what conditions need to be fulfilled such that I get a similarity solution. So let's start now to do that. So du dx, that's certainly something that appears here, for instance. Here I have that, or actually here. So du dx, that is obviously the derivative in x of u. And u, we know now from this equation, is nothing else than f prime of eta times ue of x. And now I can use everything I know about derivatives. I can just perform this derivative. It's a product, so I need to use the product rule. So that gives me ue prime as a function of x times f prime of x plus ue of x times, I need to take the derivative of this of f prime with respect to x. But of course, this is a function of eta, so I need to use the chain rule. So that becomes df prime d eta times d eta dx. I continue here. ue prime of x times f prime of x. There's not much I can do here, but here I can simplify that a little bit. This becomes ue of x times f double prime of eta times d eta dx. So this is what I can do with the derivative in x. Now I need to continue du dy. Same game here, d dy of u, which is f prime of eta times ue of x. And also this is, of course, the same product. It will be ue of x times df prime d eta times d eta dy. So that's another derivative of eta. Now realize that ue of x is actually not a function of y. So I don't actually, it's not a product. It's just one value that is dependent on y. So I'm actually already done here. So this is ue of x times f double prime of eta times d eta dy. Then the only other term that is left is d squared u dy squared, which is just one more derivative of the term that I just calculated. D dy of what I have written here, ue of x times f double prime of eta times d eta dy. And now we have actually a multiplication, and what we get is ue of x times f triple prime of eta times d eta dy squared plus ue of x times f double prime of eta times d squared eta dy squared. So these are the three terms where we need to calculate derivatives. Now, if you go and look to equation number 3, this is essentially all the terms that I need. Everything else I can just put in. There is a slight issue with this integral, which we'll now look at in the next step. But for now, we can take all of these terms, and we can put them all in equation 3. Put all in equation number 3. And there will be a little bit of writing now. As I said, I tried to do it as good as I can. So we have ue of x times f prime of eta. That needs to be multiplied with ue prime of x times f prime of eta plus ue of x times f double prime of eta times d eta dx minus, now comes this integral term, d dx of the integral from 0 to y of ue of x times f prime of eta dy. And this needs to be multiplied with ue of x times f double prime of eta times d eta dy. Because this should be a double prime here. Just make sure that this is really so. Okay. So this was the left side, and now the right side becomes ue of x times due of x dx. That was the pressure term, plus nu times, now comes the second derivative, ue of x f double prime, no, triple prime of eta. Then we have d eta dy squared plus ue of x times f double prime of eta times d squared eta dy squared. Okay, so now we have all of these wonderful terms. Now we realize, of course, that there is now different orders of derivatives of f in here. So we have here, for instance, f triple prime. We have f prime. We have f double prime, and so on. So there's a there's a number of different terms that appear here. So that means we can now try to sort all of these terms in a kind of a more convenient way in order for us to recognize the structure of the equations in a slightly better way. Which means, so if I'm taking away these colors, so if I'm doing that, what I can get at the end, if I'm just isolating, I'm focusing on this triple f triple prime term. If I'm just rewriting or multiplying everything in such a way that this one is actually standing alone, f prime of eta is standing alone, then I can essentially put down all the terms in such a way that this one is alone. So essentially, it means I divide by nu ue of x and the second derivative of eta with respect to y. So what I get then, f triple prime plus f double prime of eta times d squared eta dy squared dividing by this d eta dy squared term. So that was essentially the f double prime term that I have. If I then continue, this gives me on the other side f of eta times f double prime of eta times ue of x divided by the viscosity times d squared eta dx dy. And then here I have d eta dy to the power of 3. And I have one more term, that is f prime squared of eta minus f of eta times f double prime of eta minus 1 times due of x dx times 1 over d eta dy squared times 1 over u. So these are now all these terms written up. I guess the only relevant I guess we can essentially recognize all the terms that we have. So, for instance, I mean, essentially, we can see all of those. We have the various f double prime, etc. Terms appearing here. Now, the interesting aspect, and that's, I guess, where the crucial bit comes, we have not yet defined what the eta really is. We don't know what the eta is as a function of x and y. This is something that we need to see later on. But what we have seen here is if we would reach a self-similar solution, then it means that this equation, the one that I wrote now in terms of f triple prime, f double prime, and f prime, that this equation actually needs to be in such a way that all the coefficients that we have, that means this coefficient, that means this coefficient, and this coefficient, so these three coefficients, which I can call G1, G2, and G3, that these needs to be non-dimensional. Or non-dimensional in a sense, these three terms, they can only depend on eta, but not on x and y. Because if they depend on eta, then my whole equation is written in f and eta, and then I have a self-similar solution. If there is still some x and y's left, then my solution is not self-similar because there is an additional dependence on x and eta, which is not accounted for by my similarity transform. So that is actually quite an important statement here, that I need to realize that I need to look at these coefficients G1, G2, and G3 for this to allow for self-similarity. And what I wanted to say before, of course, now realize, we talked about this term here, so the integral, and of course now you start to realize why I'm actually interested in having, why I was interested in having an f, in having f prime here rather than f, because that term, or this term here, is the one that actually transforms into these two f terms. So I'm actually going back from f prime to f, because you realize here that's an integral with respect to y, and the ue that of course comes out. But what is then left here is essentially an f prime integrated with respect to eta, or with respect to y. Therefore, we have this this f term and not the f prime term. So that explains why my u velocity was defined as f prime rather than as f before. Okay, but now the important realization here is that for self-similarity, the three coefficients, G1, G2, and G3, they can only depend on eta, but not on x and y. Because it's only then that my solution is actually self-similar. And if you're unsure about that, go back to the example with Stokes' first problem, where he realized that our transformed diffusion equation was exactly of that form. So in this case, if this is then true, then my equation that I wrote down here, which I would call equation number 4. So then equation number 4 is then only in f and eta, and not in x and y anymore. That's exactly the crucial bit. So that means we actually need to look at this G1, G2, and G3 a little bit in more detail. And this is exactly what we do after the break. So for now, let's take another 15 minutes break, and then we continue to look at G1, G2, and G3 to understand under what conditions we can actually fulfill the requirement that we have.